A NASA spacecraft is set to make history today, getting closer to the Sun than any other human-made object. The Parker Solar Probe must survive the radiation and extreme temperatures it will encounter to solve some of the mysteries about our star. In a revelation that intrigued the scientific community and captured imaginations worldwide, NASA recently highlighted advancements in propulsion technology that push the boundaries of what was once thought possible. They've developed experimental propulsion systems, such as advanced ion drives and the X-59 QSST's quiet supersonic technology that could significantly enhance space and atmospheric travel. The announcement didn't come with fireworks or a grand unveiling, but with the quiet precision that often accompanies significant scientific progress. The implications, however, are far-reaching. For decades, light speed has remained the ultimate cosmic speed limit, a barrier that has confined human travel to the slow crawl of chemical rockets and ion drives. These advancements suggest that limit may be better understood, though not yet surpassed. If you enjoy this content, please give it a like and subscribe for more updates. The roots of these advancements stretch back years, hidden within the research halls of experimental propulsion projects like the X-43A and other innovative concepts. Whispers of advanced propulsion, such as nuclear thermal propulsion and electromagnetic drives, have floated through NASA white papers and technical journals, often considered long-term possibilities. Behind closed doors, a dedicated team of physicists, engineers, and visionaries has been exploring these frontiers. The newly highlighted technology, previously discussed in theoretical terms, appears to be a form of propulsion that improves efficiency and speed within the constraints of known physics. A system that enhances spacecraft performance, though it does not yet bend the rules of motion itself. NASA's updates focus on a practical framework that has long been explored by engineers: the optimization of propulsion through advanced physics. By improving energy efficiency and thrust, a spacecraft could travel farther and faster using less fuel, enabling extended missions within our solar system. This concept, distinct from speculative ideas like the Alcubierre drive, remains grounded in current technological capabilities. NASA's engineers are refining these systems, addressing challenges like energy efficiency and thermal management without requiring theoretical leaps beyond current physics. At the heart of these developments is what's being called advanced propulsion technology, a category of systems unlike traditional engines. Rather than relying solely on combustion or electromagnetic propulsion, these technologies, such as ion propulsion used in missions like Dawn, generate efficient thrust for deep space exploration. The result is enhanced mission capability without defying physical laws. From within the spacecraft, the system operates within the principles of Newtonian and relativistic physics. This has two significant implications. It allows for longer missions, such as those to the outer planets, and improves the feasibility of crewed missions to Mars. The ramifications of these technologies are profound. The speed of light, nearly 300,000 kilometers per second, remains the ultimate barrier to interstellar travel. To reach even the nearest stars with existing propulsion systems would take tens of thousands of years. But systems capable of optimizing travel within our solar system change mission profiles significantly. Alpha Centauri, just over 4 light-years away, remains out of reach for now, but enhanced propulsion could make missions to the outer solar system, like Jupiter or Saturn, more practical within a human lifetime. Beyond our solar system, these technologies could improve our understanding of the universe itself. With more efficient propulsion, humanity gains tools to conduct deep space exploration at an improved scale. Planets once thought challenging to reach become more accessible. Entire regions of the solar system open up for study. More than that, the nature of mission planning, fuel efficiency, and spacecraft design must be re-examined. While time dilation remains a factor only at relativistic speeds, these advancements reduce travel times for interplanetary missions. The possibility of human settlement within our solar system is no longer a distant dream in this new context. With improved propulsion, exploration of Mars or the moons of Jupiter becomes a matter of logistics and engineering rather than a fundamental limitation of physics. Advanced telescopes have already identified potential targets for study, some in habitable zones, like Mars or Europa. If advanced propulsion systems can be scaled efficiently, fleets of exploratory probes could expand the search for resources and scientific data within our solar system. There is also the question of energy, a key challenge in propulsion development. NASA's updates hint at improvements in energy efficiency, possibly involving advanced solar electric propulsion or nuclear thermal systems. These concepts suggest more sustainable power sources for long-duration missions. If mastered, this would not only power spacecraft, but could enhance global energy research, though not yet replacing fossil fuels or nuclear plants entirely. Furthermore, the emergence of advanced propulsion ushers in a new era of strategic and scientific considerations. A civilization capable of efficient interplanetary travel possesses enhanced capabilities for exploration and resource utilization. Satellites and probes could be deployed across the solar system more effectively. Resources from asteroids and distant moons could be studied and potentially mined. Communications could be improved with faster, more efficient spacecraft, though still bound by the limits of electromagnetic transmission. From a scientific standpoint, the ability to deploy advanced propulsion enables experiments and observations that were previously challenging. Astrophysicists could study planetary atmospheres up close. Probes could be dispatched to explore moons like Europa or Titan in greater detail. Questions about the composition of the solar system, potential for life, and planetary formation could yield new answers. Yet, perhaps the most transformative implication lies not in what these technologies allow us to do, but in what they force us to consider. The universe is vast beyond comprehension, and if we improve our ability to explore our solar system, others may be pursuing similar advancements. The Fermi paradox, the question of why we haven't encountered alien civilizations, takes on new weight. Are we about to discover evidence of life within our solar system simply because we now have better tools to see it? Or are we still alone, the first to explore these frontiers? The societal impact will be no less significant. Humanity's perspective on its place in the cosmos will shift as we explore farther. The pale blue dot, once an isolated haven adrift in a vast ocean of space, now becomes the starting point of broader exploration. Philosophies, religions, and worldviews may be challenged and redefined. The notion of home may expand to include the solar system. And with it, our identity as a species may undergo a transformation. Meanwhile, the technical community will face the task of making these technologies safe, scalable, and economically viable. Translating prototypes into functioning systems will require new materials, design principles, and engineering advancements. Safety protocols for long-duration missions, shielding against cosmic radiation, and managing extended spaceflight will need further development. Education systems may adapt to accommodate this leap. Future generations might study propulsion mechanics that optimize interplanetary travel. The role of engineering will become ever more central to space exploration. Partnerships between academia, government, and industry will be essential in fostering the collaborative environment needed to bring advanced propulsion into widespread use. Of course, there will be skepticism. Claims of revolutionary propulsion challenge current engineering limits. Critics will demand replicable data, peer-reviewed publications, and independent verification. These are reasonable demands and crucial for the integrity of science. Yet, the fact that NASA, a conservative and highly respected institution, has acknowledged progress in propulsion lends credibility to these efforts. The barrier of efficient interplanetary travel has been a defining limit of human aspiration. Advancing it is akin to when early humans first harnessed fire or when flight became reality. It changes what we think is possible. It alters the scale of our ambitions. It invites us to imagine futures that once seemed distant. From Mars, bases to asteroid mining, from planetary science to solar system exploration, an advanced propulsion-capable civilization enters a domain of new possibilities. In the coming years, every facet of these systems will be scrutinized, tested, and debated. But their existence, even in early stages, marks a threshold moment. The next century may not be defined by interstellar conquest, but by our mastery over solar system exploration. And once those limits are pushed, everything else becomes a matter of time. Time, which was once a constraint in space, may now become an ally. Distances that once took years to cross could shrink to months. The planets, long studied from afar, may become destinations on a map. Human beings, confined for eons to a single planet, now stand on the precipice of a journey across the solar system. A voyage not just to other worlds, but to the edges of knowledge and discovery. Advanced propulsion is more than a technological triumph. It is a scientific awakening, an engineering milestone, and perhaps most profoundly, a human milestone. It tells us that the solar system is not closed to us, that we were never meant to remain on Earth forever, that the future, for all its uncertainty, is not limited by the speed at which we can dream, but by how boldly we pursue those dreams. And with these new developments, it seems the dreams are catching up with the planets. NASA's advancements in propulsion represent a turning point in human exploration. But the ripples they will send through every domain of civilization are only beginning to be understood as the technologies move from prototype to application. The scale of transformation they promise is significant, not just in how we travel, but in how we conduct science, approach governance, and conceptualize our place in the cosmos. With progress in propulsion, humanity stands on the threshold of its next exploratory leap, not interstellar, but interplanetary and existential. What follows is not merely the excitement of extended travel. It is the construction of infrastructure to leverage interplanetary mobility. Earth-based infrastructure would need to evolve in scope. Orbital platforms could become vital nodes of production. Modular spacecraft fitted with advanced propulsion and constructed in orbit might replace traditional rockets. These stations could serve as Robin Hood as hubs for scientific missions or resource exploration. Logistics would be revolutionized on a scale that transforms space exploration. Supply chains could span planets rather than countries. Valuable resources buried in the gravity wells of moons or asteroids could be studied and transported. Elements rare on Earth, such as helium-3 from lunar regolith, might spark new industries. The material wealth of the solar system could become accessible within practical timeframes. With such potential, competition among nations and private entities would intensify. While NASA's advancements mark a breakthrough for the United States, they will spark a race for influence and exploration. Governments and corporations will adapt these principles, triggering investment and innovation. The new space race would be about who explores the solar system most effectively and what discoveries they claim. This geopolitical dimension carries risks and opportunities. The ability to send craft across the solar system presents challenges that current international law cannot address. The Outer Space Treaty of 1967 prohibits sovereign claims over celestial bodies, but never imagined widespread exploration. A redefinition of space law would be required to prevent conflicts, enforce ethical conduct, and regulate resource use to avoid exploitation. Moreover, the social consequences on Earth would unfold as the implications of interplanetary reach settle in. As people absorb the fact that destinations like Mars are reachable, a cultural reorientation will occur. Ambitious individuals may seek new frontiers, like oceanic explorers centuries ago. Families, scientists, entrepreneurs, and artists might relocate to orbital stations or planetary bases. The first wave of interplanetary explorers would represent humanity's values, dreams, and ambitions. New cultures forged under distant skies would form independently. Education systems would adapt swiftly. Children born today could grow up in a world where careers involve navigating interplanetary routes or designing lunar habitats. New fields would emerge: space navigation, planetary ecology, and astrogovernance. Universities might open orbital campuses, offering courses in applied space engineering. A renaissance of learning may ignite on a scale not seen since the Enlightenment. Human physiology will become a primary concern. Advanced propulsion may reduce travel times, but cosmic rays, low-gravity environments, and long missions will require new medical fields. Genetic engineering, cybernetic enhancements, and regenerative therapies may adapt humans for spacelife. The definition of humanity may evolve. And then there is time, not relativistic, but logistical. With shorter travel times, mission schedules may shift. A person could travel to Mars and return within months, not years. This will affect families, careers, and governments. People may choose between earthbound lives and spacefaring ones. This could create distinct classes: Terran and interplanetary. Economically, advanced propulsion could birth new markets and disrupt others. Earthbound industries may shift to zero-gravity manufacturing or asteroid mining. Real estate could expand to orbital habitats or planetary settlements. Currencies may evolve for interplanetary trade. Blockchain and quantum-secure systems could form an interplanetary financial backbone. Scientific research would accelerate. Mobile observatories could explore planets firsthand. Experimental science could involve active missions to test theories of planetary formation or life's origins. Gravitational fields and cosmic phenomena would become practical study objects. Philosophy and theology will face challenges. Exploring habitable worlds could shift beliefs about humanity's uniqueness. Concepts of destiny and divinity may be reinterpreted in an interplanetary context. Faiths may find new meanings or debate the ethics of colonization. Art and culture would flourish in new directions. The Apollo missions inspired art. Advanced propulsion could ignite genres centered on the experience of space travel or alien landscapes. Spacefaring cultures may develop unique aesthetics shaped by their environments. Storytelling could evolve, echoing across planets. Artificial intelligence and robotics will be crucial. The human mind may need AI co-pilots or autonomous systems for complex navigation. Advanced AI may lead exploration, preparing environments, or initiating contact with potential life forms. Machine-led exploration could align with propulsion advancements. Communication across vast distances will prompt innovation. Even at high speeds, signals take minutes to travel. New protocols, possibly quantum-based, would maintain cohesion among colonies. Delays could become normal, requiring new forms of diplomacy. Ethical questions will multiply. Who decides exploration targets? What rights do colonists have? Are we entitled to alter alien ecosystems? What if we find life or extinct civilizations? How should we respond? Cautiously, reverently, or assertively? These decisions must be addressed before the first major missions. The concept of extinction takes new meaning. Humanity could establish colonies across the solar system. A solar flare or asteroid impact would no longer end the species. This redundancy mirrors biological survival strategies. Yet, this dispersal could fracture identity. Humans separated by vast distances may diverge in language, culture, and biology. In 1,000 years, humanity may become a family of species linked by a common origin. This divergence must be embraced with humility and foresight. The environmental impact could be positive. As industry moves off-planet, Earth could heal from resource extraction and pollution. The planet might become a sanctuary. Environmentalists may advocate for space exploration to preserve Earth. All of this assumes the propulsion systems can be scaled. If so, the next few decades will bring unprecedented progress. Advanced propulsion is a beginning, a doorway to diverse futures. The solar system, once a distant frontier, may become navigable. NASA's advancements have reignited our aspirations, changing how we see our place in the cosmos. The stories of exploration, Mellon, Columbus, Armstrong, are opening lines of a longer narrative. The next chapters will be written on Martian plains, in lunar orbits, and on distant moons. For now, advanced propulsion remains in development, years from deployment. But the blueprint is there. The knowledge has been unearthed. The barriers of distance have shown cracks. And in those cracks, humanity glimpses a canvas vast enough to hold our ambition, curiosity, and spirit. The journey ahead is not just one of distance. It is a journey of transformation, of becoming more than we were. Faster, wiser, more unified, and courageous. In exploring the solar system, we carry Earth with us as its messengers, guardians, and promise. Advanced propulsion is not the end. It is the beginning of everything else. One of the overlooked aspects of NASA's propulsion advancements lies in its psychological and cognitive ramifications. Human consciousness evolved within Earth's sensory limits. Navigating space introduces new perceptions. What will it mean to see planets up close or experience long missions? Advanced propulsion will alter not just what we do, but how we perceive reality. This shift may inspire cognitive training programs to adapt to space environments. Travelers may need to recalibrate instincts as Newtonian motion shifts. Visual input will change due to cosmic conditions, possibly requiring augmented reality to translate the alien into the familiar. Neuroscience will emerge as a key discipline. Researchers will study how memory, emotion, and cognition respond to space conditions. Do people age cognitively differently in space? Do sleep patterns shift? Could memory encoding change? Answers will inform spacecraft design and crew support systems. The nature of history will change. Historical records, once linear, will face asynchronous timelines across colonies. Historians will contend with differing chronologies. Archival systems may adopt quantum synchronized time indices for cohesion. This raises philosophical questions about identity. A person could travel to Mars at 30 and return biologically older, while Earth ages further. Reunions will be bittersweet. New forms of grief, nostalgia, and dynamics will emerge. Literature and art will explore temporal dislocation and lost futures. The definition of community will evolve. Chronological communities may arise, connected by shared timeframes across distances. Time zones may define identity in the interplanetary age. Governance and politics will be redefined. Democracies rely on shared geography and time. How can laws be enforced across planets with delayed communications? Colonies may require semi-autonomous systems, guided by AI or flexible frameworks. These may resemble city-states connected by federations. Political scientists will envision governance resilient to dispersion, yet cohesive to prevent conflict. A new federalism may emerge, based on principles and timelines. If you like this video, please give it a thumbs up and subscribe to our channel. Share your thoughts on NASA's propulsion advancements in the comments below. Do you believe they'll transform exploration? We'd love to hear from you. Thank you for watching, and see you next time.